The second proof I'm going to do on logarithms is called the base change. This proof, well, this property is very nice because unfortunately your calculator has not had a lot of programming upgrades in the last 20 years, and it cannot handle anything besides base 10. So many times when working with logarithms we have to do a base change. For instance, let's say I wanted to find out what exponent I put on a 2 to get 17. Well, I can come pretty close doing this in my head, but it's only a very, very rough approximation. I know 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, which is just below it. 2 to the fifth is 32. So I know my answer is just going to be a hair over 4. Maybe 4.1. Problem is, I can't get a very good approximation. The calculator can do a much better approximation after we do a base change. So, to use our calculator, we'll do the base change to base 10, plugging that in as two separate logarithms, and now it gives a much better approximation, just over 4. This is, someone have that calculation? Log of 17, close parentheses, divided by log of 2, close parentheses. What does the calculation come up to?
4.087.
About 4.087, roughly. But that's a much better approximation to get in your calculator than I can do in my head. So base change is a very nice tool to have. How do we know a base change is always going to work? To find out whether it's always going to work or not, we're going to set it up with a proof. First thing I'm going to do is talk about my left-hand side. I'm going to say that if this has a value, then that value will be some unknown amount, which I will call x. So I'm not making any assumptions about what the value is, none whatsoever. Now, my very, very first step is I'm going to take this out of logarithmic form and rewrite it in exponent form, noting that the exponent I put on a to get the value b is x. Next thing I'd like to do is talk about the property of equations. In the property of equations, if the left side and the right side are equal, I can do anything I want to one side. It will always get me the same on the other side. If I add 2 to the right and add 2 to the left, I'll get the same answer. If I divide both sides by 2, I'll still get the same answer. One other property that we have in the property of equations is if I take the logarithm of both sides, I'll get the same answer, which makes sense because they're the same value. So, the exponent I put on an n to get a to the x better be the same exponent I put on an n to get b, because a to the x and b are the same thing. Now, in my very first proof, I said that this could be rewritten. That this can be rewritten as x log base n of a. I did not change the value. I did not recalculate it. All I did was use a property that has been proven. Now, instead of the x being an exponent, the x is a product. It's multiplication. I can break the bonds of multiplication with division, which means I can get the x all by itself simply by dividing both sides of my equation by log base n of a. Notice where I started. Notice where I ended. This leads us to conclude that, in fact, log base a of b is log base n of b over log base n of a.